Hello and welcome to another lecture of analog integrated circuit design. So far we have been looking at what happens if you have a delay in a negative feedback amplifier and where those delays could come from. The delays can come from parasitic poles in the system. We also saw that a pole acts like a delay for the integrator. Okay. So today what we will do is elaborate a little bit on these things and then see how to conveniently judge the stability of an amplifier and how to design it so that it is well behaved. So, this is our negative feedback amplifier and it could have a delay Td in the feedback path or anywhere in the system. While quantifying the amount of negative feedback, we have computed the loop gain, and the loop gain of this particular system without the delay is omega u by k divided by s, which can be defined to be omega u loop divided by s. Here omega u loop is the unity loop gain frequency and it is given by omega u by k, where omega u is the unity gain frequency of the integrator used to realize the negative feedback system. Now, how much delay can we tolerate depends on the value of omega u loop. So, our previous analysis shows that for Td less than or equal to 1 by E times 1 by omega u loop, that is 1 by 2.718 times the time constant of the integrator, we get no overshoot in the step response, and essentially it behaves like an overdamped system, that is for Td less than this number, it is equivalent to an overdamped system. For Td equal to 1 by E times the time constant of the loop gain, then there is again no overshoot and this is the critically damped system. So, this corresponds to the highest delay that you can have without having an overshoot in the step response. It also corresponds to the fastest step response you can have without overshoot. So, that is why it is the critically damped response, okay, critically damped system. Now, when Td is between 1 by E times the 1 over omega u loop and between pi by 2 1 by omega u loop, what happens is there is ringing in the step response, but the ringing eventually dies out. Okay. So, the system is stable in that if you apply a step there will be some ringing and that thing eventually dies out, and the same thing is true if you have initial conditions in the system, they will eventually die out, but there can be a lot of ringing. You can tolerate a little bit of ringing, but usually not a lot of ringing. Okay. And for Td more than 1 by omega u loop, what happens is there are sustained oscillations. Okay. So, that means that if you apply a step, then there is ringing and it blows up. Also, if you have some initial conditions, they will not die down, they will eventually blow up and give a response even without having an input. So, this is an oscillatory condition and this is certainly something that you do not want to have. Okay. And for a good amplifier, that means a well behaved amplifier, you can tolerate a little ringing. It also depends a little on the application that you are looking at. You can tolerate a little ringing. So, typically TD less than about half of 1 by omega u loop is tolerable. Now, if your application says that there has to be absolutely no ringing at all, then you have to make TD to be less than 1 by E times 1 by omega u loop. Okay. So, this is what is tolerable, and if you have TDs beyond this, it will start ringing more and more, and if you have TD more than pi by 2 times 1 by omega u loop, you will have sustained oscillation, and certainly you do not want to have that. Okay. So, now let us see what happened when there was an extra pole and related to this one. What we said was there was extra pole in the loop somewhere. We have not actually looked at exactly where it can be, and it can come from parasitic capacitances at various points in the circuit. So, for now we will simply model it as our usual system, an integrator with a unity gain frequency omega u, a voltage divider of fraction 1 by k, and here I will simply have an ideal block which models the pole. Okay. Just like the delay, it does not matter where in the loop this pole is. So, as long as it is in the loop, it will affect the response of the system. So, the first thing is we see that the step response of the loop gain without this extra pole will be a ramp whose slope is omega u by k or omega u loop. If you have an ideal delay of TD, then the step response will have the same slope, but is delayed by an amount TD. This corresponds to a delay of TD. And finally, if you have a pole, if you have a extra pole P2, what happens is that you will also have something like this, and the response slowly rises, but eventually it will settle to a slope which is the same as for the other cases, it is equal to omega u by k. The slope is omega u by k, and it is shifted horizontally by an amount that depends on the pole, and in fact it is exactly equal to 1 by P2. Okay. So, a pole P2 is approximately the same as a delay of 1 by P2. Okay. So, we can expect a similar behavior, that we know that if the delay is very small, there will be no overshoot in the response. As the delay becomes larger and larger, there will be overshoot. Similarly, if the pole P2 is very large, which corresponds to a small delay, there will be no overshoot, and if the pole P2 becomes very small, then you will start having overshoot. And in fact, we have already analyzed this through the damping factor, and we have seen that for this particular system the damping factor will be half square root of the unity loop gain frequency divided by the parasitic pole P2. Now, for no overshoot we need to have damping factor equal to 1 or more. So, that means that the pole P2 has to be at least 4 times greater than the unity loop gain frequency. I made a mistake in this expression, this has to be P2 divided by omega u by k. So, the damping factor will be more than or equal to 1 if P2 is greater than or equal to 4 times omega u by k, and this is consistent with the notion that a pole is similar to a delay. A pole at P2 corresponds to a delay of 1 over P2. So, if the pole is at a very high frequency, the delay is very small and there is no effect on the step response. If the pole comes lower and lower in frequency, then there will be an effect on the step response in that it will start ringing. Okay. And the critically damped case, zeta equal to 1 corresponds to P2 equal to 4 times omega u by k, and you do not want to have a pole that is substantially lower than this in frequency. Okay. Now, one thing about the system with the pole that is different from the system with the delay is with a single extra pole P2, the system is unconditionally stable, meaning there can be ringing in the system, but there will never be a sustained oscillation. This is because it is a second order system and that is what it turns out to be. We will see that when you have multiple extra poles, this is no longer the case. Firstly, the system is unconditionally stable. The system is critically damped for P2 equal to 4 times the unity loop gain frequency, and the system is over damped for P2 equals P2 more than 4 times unity loop gain frequency. Okay. So, now again we can tolerate this condition, we can violate it, we can violate this condition a little bit, but not by too much. Okay. It is okay to have, let us say P2 is 2 times omega u loop, in this case you will get a little ringing, but certainly you do not want to make P2 at a lower frequency than this. In that case you will have a lot more ringing and it will not be acceptable in an amplifier. Okay. Now, this shows that with an extra pole the system behaves as though there is an extra delay, and the conclusions that we drew from the original analysis with the delay holds good even now. Just to reinforce this notion and to connect to the analysis we are going to do later, which will make this solution to the whole problem easier, we will do it for 2 parasitic poles. Okay. We will assume that the negative feedback amplifier has okay. I have assumed 2 extra poles somewhere in the loop. Okay. So, what happens in this case is the step response without the parasitic pole of the loop gain will be a ramp whose slope is omega u by k, and with this parasitic delay it will initially do something, but finally settle to a ramp with the same slope and a delay of 2 over P 2. Okay. In fact, if you have multiple poles in the system, each pole can be thought of as contributing a delay of 1 over that pole. Okay. So, this is the unit step response of the loop gain, and it again acts as a delay. So, for this particular case we will try to solve for the condition when there will be sustained oscillation, just to see what happens when we go to higher and higher order systems. Okay. So, V naught by V I will be equal to the gain of the forward path plus divided by 1 plus the gain of the forward path times the gain of the feedback path. This you can work out for yourself, even if you do not know the formula. By writing out the variables around this loop, you will be able to work out this, and this can be rewritten as in the standard form by multiplying by 1 plus S by P 2 square times S by omega u by k. Okay. So, we will get this is what we will get, and I will for convenience I will replace this by a variable omega u loop. Okay. And now you can clearly see that as we go to higher and higher order systems, evaluating the step response in a closed form and finding out whether there is ringing or not becomes very difficult, which is why we will later go to a more convenient condition in which we do not have to solve for it analytically. Okay. So, but we will look at the condition for which this system is unstable. Okay. An unstable system means the poles are on the j omega axis. Here when I say poles, I am talking about poles of the closed loop system are on the j omega axis or in the right half plane. Now, it turns out that it is rather easy to solve for the condition where the poles are on the j omega axis, and that is what we will do. When the poles are on the j omega axis, what happens is, for a certain frequency s equals j omega, this expression V naught by V I becomes infinity. Okay. For this condition, V naught by V I is infinity for some s equals j omega. Now, if we had a single extra pole P 2, this would never happen, but for more extra poles this can very easily happen. Okay. So, how do we solve for it? We will set the denominator to be equal to 0 for some s equals j omega. Okay. So, what I have to do is I have to substitute s by j omega in this expression and set the result to 0. Okay. So, as usual I encourage you to try this out before you look at my solution and find the condition for which it happens. Okay. This is 0 for some s equals j omega, okay, and this is nothing but again for s to be j omega. So, this means that minus 2 omega square p 2 omega u loop plus j omega by omega u loop plus 1 equals 0. So, as you can see there are two variables here, the value of omega for which this happens and the condition on p 2 at which this happens. Okay. And there are two equations because there is the real part of this equation and there is also the imaginary part of this equation, and each of them has to be equal to 0. By equating them to 0 you will get the two conditions. Okay. Firstly, if you equate the real part to 0 you will get 1 minus 2 omega square divided by p 2 omega u loop equals 0, and if you equate the imaginary part to 0 you will get minus omega cube by p 2 square omega u loop plus this part omega by omega u loop equals 0, and this gives you omega to be equal to p 2. Okay. And if you substitute it here you will get, substituting this in the first equation you will get p 2 to be omega u loop divided by 2 for the condition to hold. Okay. Just to summarize, what we have done is we have evaluated the closed form transfer function and we have found out the condition under which this becomes infinity. It becomes infinity when the denominator becomes 0, and we have evaluated some s equals j omega for which this can happen. So, what it says is when you have two parasitic poles at the same frequency, mind you I have in this case taken both the parasitic poles at the same frequency. This is for convenience of analysis, it does not mean that in reality it has to be always that way, but the conclusions we draw from this will hold for the general case. When there are two identical parasitic poles at p 2 and then when p 2 happens to be half of the unity loop gain frequency, the gain will be infinity for omega equals omega u loop by 2. Okay. Now, it actually does not matter for what frequency the gain becomes infinity, because once the gain becomes infinity at certain frequency, at that frequency even without an input you will have an output. So, the amplifier becomes completely unusable, because the amplifier is supposed to give you only the input times the gain, it should not have anything unrelated to the input. But if the system is unstable, it will have something that is unrelated to the input and the amplifier is useless. Okay. So, this is the condition, and it can also be shown that if P 2 is smaller than this, the output blows up. Okay. If P 2 equals this, you will have a sinusoid at the output even without an input, and it will be constant in amplitude, and if P 2 is smaller than this, the ringing or the sinusoid will keep growing in amplitude and will never die down. So, for stability, P 2 should be less than half of the unity loop gain frequency, and when P 2 equals the unity loop gain frequency by 2, the poles of the closed loop system are on the j omega axis, and when P 2 is more than omega u loop by 2, closed loop poles are in the right half plane, which also means an unstable system. Okay. So, just as before, when P 2 becomes very small, the equivalent delay becomes very large and the system becomes unstable. Okay. So, we can carry this exercise for 3 extra poles and 4 extra poles and so on, and it is most convenient if you assume that all the parasitic poles are in the same location, but the conclusion that you draw from this is general, even if you have poles at different locations, the total delay contribution due to all the poles should be limited to a certain value. Okay. If the delay becomes too much, the system will become unstable. I will quickly tabulate the results. Okay. So, let us say we have the case where there are no extra poles. Okay. And this is the ideal case that we had considered, and in this case the loop gain is omega u loop by s or omega u by k divided by s. Let me write it more clearly. If you use an integrator of unity gain frequency omega u and make an amplifier with a gain of k with it, it will have a loop gain like this, which corresponds to omega u loop by s, and this will actually never ever become unstable, it is unconditionally stable. Okay. It is a first order system with a pole at omega u by k, and it is unconditionally stable. So, let us say you have one parasitic pole at a certain frequency P 2, the loop gain function will be omega u loop by s 1 by 1 plus s by P 2, and actually even this never becomes unstable, but it does get underdamped or shows ringing if P 2 is less than 4 times the unity loop gain frequency. Okay. and similarly you can have two parasitic poles both identical at P2. In this case the loop gain function is this, and you can calculate when it becomes unstable, and it becomes unstable for P2 less than 0.5 omega u, and you can do it for 3 parasitic poles at P2 and this is the function, and this becomes unstable for P2 less than 1.16 omega u. Sorry, 1.13 omega u, and finally you can also try 4 and 5 and how many ever you wish to have, and here also the system can become unstable. This is the function, and this becomes unstable for P2 less than 1.76 omega u. Okay. So, to summarize, an extra pole is like a delay, and as the delay increases you will tend to have ringing in the system, and when the delay increases a lot you can even have instability. That means the system can give you an output even without an input. You can think of it as the gain becoming infinity at some particular frequency, or the poles being in the right half plane. Okay. Now, it turns out that for the special case of a single extra parasitic pole, the system is never unstable. It can ring, but it is never unstable. Okay. So, you still have to make sure that the parasitic pole is at a high enough frequency to ensure that the ringing is limited. Okay. And that limit is usually 2 times the unity loop gain frequency, and if you do not want any ringing at all, the parasitic pole has to be at least 4 times the unity loop gain frequency. Okay. Now, you can have 2 or 3 or 4 or extra parasitic poles, and they can be at various locations, but for analysis it is easiest if you assume that all of them are at the same location. If you have 2 identical parasitic poles P2, what happens is the system can become unstable, and it happens for P2 lesser than 0.5 omega u loop. Okay. So, all of these I have written here should be omega u loop, 0.5 omega u loop, and for 3 extra parasitic poles it is 1.13 omega u loop, and 4 of them it is 1.76 omega u loop. Now, the other thing you also notice is that when you increase the number of poles, the permissible location for the pole is at a higher frequency. For instance, with 2 parasitic poles it is at half of omega u loop, and with 4 parasitic poles it is at 1.76 omega u loop. This is because each pole contributes a certain amount of delay, and when you have multiple poles the delays due to each of the poles adds up. Okay. So, it effectively constitutes a greater delay. So, the delay due to each pole should be smaller if you have to ensure stability. Okay. And this can be easily related to the first result that we had obtained, that if you have an ideal delay and if the delay becomes too much, that is 1.5 times 1 by omega u loop, the system becomes unstable. It is exactly, it is pi by 2 times 1 by omega u loop, which can be approximated to 1.5 times 1 by omega u loop. Okay. So, the greater the number of poles, the higher frequency they have to be. If they come to lower frequencies, you will risk instability. Okay. Now, what we are interested in amplifier design is not merely avoiding instability, because it can be ringing a lot which dies down, the ringing dies down and it is still a stable system. That is also not what we are interested in. What we are interested in is also a well behaved system where it does not ring too much. Now, what happens is when you have multiple poles, evaluation of the step response becomes difficult. When we had only one extra pole, it is very easy. We know the step response of a second order system, and we can classify it into critically damped, over damped and under damped, and we can easily identify the condition for which there is no ringing, that is, it has to be critically damped or under damped. Now, when you go to higher and higher order systems, this is not the case. Okay. The analytical expressions become too complicated and it will become simply too difficult to judge even stability, or it is even more difficult to judge when the system is well behaved. So, what we will do is we will not evaluate the transfer function and work with the polynomials, which is very difficult. What we will do is taking our hint from the ideal delay case for which we have a solution and the second order case for which also we have a solution. From there we will extrapolate some conditions for higher order systems, and these conditions will not be based on calculating polynomials and their roots etc., because that is what is very complicated. It will be based on evaluating the polynomial for some sinusoidal frequency, that is evaluating the sinusoidal steady state response of the loop gain. Because of that it is much easier, and that is the preferred way of analyzing negative feedback systems. Okay. The closed form expressions for step response are too complicated for higher order systems. So, which basically means that we need an alternative method for analysis. Okay. And there is an alternative method that does not depend on calculating the denominator polynomial and its roots and so on, and that is based on the Nyquist criterion. So, the Nyquist criterion would be familiar to you from courses on control systems. In this course we are not going to deal with the proof of the Nyquist criterion and so on, but we will just state the Nyquist criterion and use it for our purpose, which is to be able to design well behaved amplifiers. Okay. So, just to start off with, we will take the classical representation of the feedback amplifier, which also includes the amplifier that we have derived. And if you look at control systems textbooks, this is how it is written. The forward path is denoted by G and the feedback path is denoted by H. Okay. And for our prototype case, G is nothing but the integrator and H is nothing but 1 by K ideally. I mean, in reality there will be parasitic poles in either G or H or both. Okay, there will be extra poles in the system. So, this V naught by Vi, as we know, has an expression G by 1 plus Gh, where this Gh is nothing but the loop gain. As we have seen, the loop gain is something that we use to quantify the amount of negative feedback. So, the way we do it is by breaking the loop somewhere, applying a signal in the forward direction of the loop and see what comes back. Okay. For instance, in this particular case, we can break it here. We set the input to 0 for evaluation of the loop gain, because we are not interested in any particular input, but we are only interested in what comes back around the loop. So, we can apply some V test here, and what comes back here we know is minus Gh times V test. So, this Gh is defined to be the loop gain. The minus sign is omitted because we assume that we are making a negative feedback amplifier. So, we expect a minus sign and that is omitted, and Gh is the loop gain. Okay. And as you can see from this expression, the gain will become infinity if GH becomes minus 1, okay, if the loop gain becomes minus 1. So, the stability criteria usually revolve around the loop gain and the value of minus 1, that is you should not have a loop gain to be equal to minus 1. So, how to avoid it and what to do with the loop gain, that is what the stability criteria work with. Okay. So, in a very crude way we can say that stability criteria is about avoiding GH being minus 1. There is a little more to it than that, but that explains the significance of minus 1 in and the loop gain. Okay. Now, what is the actual definition of stability or instability rather? Instability means the transfer function V naught by Vi, which is G by 1 plus Gh, has some poles in the right half plane. Okay. So, if this is the S plane, instability means there are some poles in this half of the plane, okay, in the right half plane. Or on the imaginary axis. Okay. So, this includes the imaginary axis. Now, it turns out that for this to work out this thing, you need to obviously calculate the V naught by Vi, and there will be some denominator polynomial. You have to find out the roots of the denominator polynomial and see whether they have positive real parts or not. If they have positive real parts, they will be in the right half plane and the system is unstable, but that is what we said was very difficult. Okay, that is very difficult because you will end up with a high order polynomial and for which the roots are not very easy to determine. Okay. So, the alternative is to use the Nyquist criterion, which states the following. Okay. So, what you can do is, instead of evaluating G by 1 plus Gh and working with the polynomials, you can simply evaluate Gh, okay, and that too not everywhere, but on the imaginary axis S equals j omega. This essentially means that what you are evaluating is the sinusoidal steady state response of the loop gain function. Okay. S equals j omega corresponds to a sinusoid of frequency omega, and g of s h of s at S equals j omega corresponds to the loop gain for a sinusoidal frequency of omega. Okay. So, you can evaluate g of s h of s and plot its imaginary part versus the real part. So, instead of calculating the polynomials, we simply calculate g times h for sinusoidal frequencies S equals j omega, and then plot the imaginary versus real. Okay. We will later go into how this plot exactly looks like. Like I said rather vaguely, that stability criteria involve avoiding the loop gain being minus 1. So, this minus 1 0 is a critical point in this whole technique, and what the Nyquist criterion states is that the plot of imaginary part of the loop gain versus the real part of the loop gain should not encircle minus 1 comma 0. that is the plot can be something like this, okay. And if it is like this for negative frequencies, it will be the mirror image. So, in this case it is not enclosing -1 0, we will make more concrete the definition of what enclosing means, but in this case you can clearly see that -1 0 is not inside this picture, okay. On the other hand, if the picture looks something like this, okay, then it looks like -1 0 is enclosed by this plot of imaginary part of the loop gain versus real part of the loop gain, which is evaluated on the j omega axis, okay. So, in this case the system will be unstable, okay. So, I have still made some vague statements, we have to make many more things more precise, which I will do, but what I would like you to do is to first appreciate the advantage of this particular technique, okay. So, before, if you had to ascertain stability, you had to evaluate this function and evaluate the denominator polynomial of that and find the roots, see if the roots have positive real parts. That is a very difficult thing to do. First of all, the expressions become very cumbersome, even for the baby cases that we took, that is you have two identical poles, you have to do a little bit of work. Now, when you have multiple poles and that too not identical to each other, it becomes very difficult. Instead, what is done is to evaluate only the loop gain and that too not everywhere, not in a general form, but on the imaginary axis, that is for sinusoidal inputs, okay. So, as you know, it is easy to calculate as well as easy to measure if you are only interested in the sinusoidal steady state response. When you have a system, you can apply a sinusoid, see what comes out and evaluate the magnitude and phase shift of what comes out compared to what goes in, okay. So, this Nyquist stability criteria is a way of ascertaining stability, that is evaluating whether the poles are in the right half plane by looking at only the loop gain, and this is a tremendous advantage, and that is why this and techniques that are sort of related to this are very widely used, okay. And roughly speaking, it involves the sinusoidal steady state response of the loop gain and the critical point of -1. And the intuitive reason for -1 being there is that if the loop gain exactly equals -1, you will have instability for sure, because V naught by Vi becomes infinity, okay. So, this Nyquist criteria says something about the plot of imaginary part of GH versus real part of GH, and make some statement which is exactly equivalent to the poles being in the right half plane. Exactly what the statement is, we will elaborate in the next class and with all the details, okay. Thank you.